Let's do activity 11, question 2. So question 2 deals with logistic regression and coming up with a good logistic regression model. So what we're going to do is just read in the reacquire data set using read.csv. And let's take a look to see what we have before us. So I'm going to look at the first few lines using head. And what we have is a data set that describes, whether or not a customer was reacquired after they churned, and we're trying to describe how this probability might be different between different customers. So based on the number of days that they were a customer originally, between the time they made their first purchase and when they left, churned essentially, the offer that was given to this customer to try to entice them to come back, the number of days that lapsed in between them churning and when the offer was given to them, the price change of the product that the customer was typically buying when they were a customer and what it is now, and then also the gender of the customer and the age of that customer. So let's see what we can do to come up with a model that describes the probability of reacquisition based on these predictors here. So doing the all possible procedure with logistic regression is typically way too slow. So what we end up doing is searching intelligently for a good model. So how do we do this? Well, what we do is we always start out by fitting the naive model and the most complex model that we want to consider. So for logistic regression, we know we need to use GLM, and in this case, we're predicting the column reacquire. And the naive model, its formula is always twiddle1. Basically, don't use any predictors. And we are using the reacquire data set. And to turn on logistic regression, we always have to put in that family equals binomial. So there's my naive model. And then let's do the full model. So what's my full model going to do? Let's consider all two-way interactions. So GLM reacquire, what we're trying to predict, twiddle dot squared. So dot squared gives you all predictors and all two-way interactions. Just twiddle dot just gives you all the predictors by themselves, no interactions. So data reacquire and family equals binomial. All right, so we fit the naive model. We fit the most complex model now. And let's conduct a search. So in our search, we have a choice of which model we want to start out with. Do we want to start out with the naive model and continue, or do I want to start out with the full model? And let's do both, because it very well could be the case that the search procedures don't converge to the same model. All right, so for the step command, the first argument is always which model I'm starting out with. The second command is always this, scope equals blah, 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 telling you the range of models that we're going to be considering. And the third argument says which direction do you want to do, and unless time's a big issue, it's always going to be direction equals both, so that we consider adding in and kicking out predictors at each stage of the algorithm. And then trace is equal to 0 here, so that the output is suppressed. And they're always going to be 0 if you end up knitting. For now, I want to do trace equals to 1 so I can actually see what's going on. So doing that forward search, we see that based on this last step, the first variable added was lifetime, then lapse, then offer, then age, and then the interaction between offer and age here. And there's nothing we can do to augment that model that drives it closer to the truth. Every step looks like it increases the AIC. All right, so that's what happens if we start out with the naive model. Starting out with the full model, and starting out by kicking out things, we might come out with something different. So we'll start out with the full model now and see what ends up happening. All right, so I'm actually going to just write a little note for myself what the AIC of this model was, 245.2. And let's see if we do any better doing the search starting out with the full model here. So this will take a little bit longer because there's a lot more models to consider here. And it looks like what ends up happening is we end up with a model with an AIC of 246.12, which is actually a little bit higher than the model started out with the naive model here. And we look like we have an additional predictor or two here. All right, so what predictors are found in the model with the naive, or starting out with the naive model? Well, I forgot already, so I'm just going to do summary of S1 because that'll remind me. And it looks like we have lifetime, lapse, offer, age, and the interaction between age and offer. What additional predictors are in the model found starting with the full model here? Well, what we see is, okay, lifetime is there, offer is there, lapse is there. Gender is a new variable, so gender is also in this model. And the interaction between offer and age was in that other model, but the interaction between gender and age is here. So the interaction between gender and age. So the other search, starting out with the full model, chooses a model with 2 additional predictors in it and actually has a worse AIC than the one started out with the naive model, so I'm actually not going to choose it. Your boss wants you to choose between these 2 models. What should you do? Well, you should probably do what I'm doing. Choose the simpler model unless you have a reason to go with the more complex model. And in this case, the simpler model is the one with the lower AIC. The one with these 2 additional predictors here, gender and the interaction between gender and age, actually had a higher AIC than the one found during the search starting with the naive model. So I would definitely go with the first model. So the one that started with the naive model. In other words, the simpler model. And it even has a lower AIC. So the difference between the 2 AICs is very small. It's less than 1 here. So from a statistical point of view, there's no valid reason for preferring one over the other. But, we have personal reasons for choosing the simpler model because it's more easily interpretable. We'd be much happier with that simpler model here. All right, so using our selected model, describe how the probability of reacquisition varies with the variable lapse. All right, so that was S1 here. So let's look at a summary of S1. And we're interested in talking about how it changes with lapse here. All right, well, the good news is that lapse is not involved in any interactions, so I can just look at the coefficient and make a comment. I see that the coefficient is negative, and so that means that customers with larger values of lapse have a lower probability of the level of interest. All right, so what is the level of interest? What is my model actually predicting? Well, let me look at a summary of the data frame once again. Our 2 levels of reacquire are no and yes. Yes comes last alphabetically, so by definition it's our level of interest. Our model is predicting the probability of being reacquired. So what we see is the rather intuitive result is that the customer with the larger value of lapse has the lower probability of being reacquired. So basically, the more time that's elapsed between the customer churning and the offer, the lower probability you have of reacquiring that customer. All right, so we see that the probability of reacquisition is getting smaller. Probability of reacquisition gets smaller when lapse gets larger. And so we see that the implication is that the longer the time between churning and when the offer is given, the lower the probability of reacquisition. And that makes sense, and that's kind of what we would expect. And it's nice that the data confirms that. All right, so a search for a descriptive model, it's failed if we didn't come up with a model that provides a reasonable reflection of reality. We always need to do that check regression step to make sure that, what we found is, worthwhile. If the assumptions are violated, then we haven't come up with a reasonable description of reality, and we failed in our descriptive modeling task. So running check regression, we see these 2 p-values. Great, they're bigger than 5%, so we passed the goodness of fit test. It looks like our logistic regression model is providing a reasonable reflection of reality. So we have the p-values of the tests are bigger than 5%, so it looks like our model does provide a reasonable reflection of reality, and it describes how p changes with the predictors. So great, we've come up with a pretty good model that we can use to describe the relationships between the probability of reacquisition and these variables here. Most importantly, it doesn't look like gender matters whatsoever. It doesn't appear in the model, and some of those other variables that are in the data frame don't matter either. So the price change, notice, doesn't appear in the model. It doesn't look like that's relevant in the probability of reacquiring that customer. Okay, so that's nice for describing what's going on, but maybe we actually want to come up with a model that will predict which customers will be reacquired and which ones aren't. We don't want to waste our time with customers that have a very, very low probability of being reacquired. So let's turn our attention to building the predictive model. First thing that we have to do is to split up our data into a training set and a holdout sample, because we need to estimate the generalization errors of all the models we're going to consider. And then once we've selected our final model, actually get a sanity check, make predictions on that holdout sample to confirm that the generalization error of that model is about what we expected. So we always want to set the seed to something before we do any sort of random thing so that we can reproduce the results. So set seed 320, train rows, this command right here. Same thing with the descriptive modeling. We're basically going to be picking rows at random from the reacquire data set. So the numbers 1, 2, 3 up to the number of rows of reacquire. And we're going to choose 60% of the numbers to be putting into the training set. So 0.6 times n row reacquire says that basically we're going to be putting 60% into the training data. So once we run train rows, we now have a random selection of rows to put into the training data. So let's put them in there. Reacquire square bracket train.rows comma is going to extract just the row numbers that are in my vector train rows, all columns, because comma blank here, and put them in the training set. And for holdout, minus train rows, we'll put the remaining rows into the holdout sample. All right, so let's do reacquire twiddle dot, basically consider all models with no interactions and see what the results turn out to be. So for a build model, our formula is always the most complex model that we want to consider. And in this case, we are always building the model on the training data, and it's a good idea to set the seed in that command as well so that we can reproduce the results. All right, so what do we see? Well, we see that as we start adding in predictors to the model has a lower and lower estimated generalization error. The model that was found with the lowest error had 4 predictors, but we can get away with a simpler model. Its error is less than 1 standard deviation above the overall lowest, so we could choose this one as well. All right, so what we're going to do is also consider interactions, because very often they do play an important role. So if we considered all two-way interactions, it would take forever for that model to run. So a strategy is to look at the variables that appear in the model with the lowest estimated generalization error and just consider interactions between those. So in this case, I'm actually going to be a little bit more strict here, save even more time by only looking at the 3 variables in the model selected by the 1SD rule. So I'm going to copy these 3 variables, and then inside the parentheses here, I'm going to separate these by plus signs. And in general, this is how you do it. If you just want to consider interactions between a subset of your variables, what you can do is within parentheses, list those variables separated by plus signs, and then outside the parentheses, do the *2. And so what this will do is it'll look at models that have lifetime, offer, and lapse in it, and then all possible two-way interactions between just these 3 variables. Saves me a little bit of time typing. Okay, so this is what we're going to consider now. All right, does any interactions help us out? And what we see is that the model with the lowest estimated generalization error doesn't have any interactions in it. It's the same one that we came out with. But it looks like we could actually get away with a slightly simpler model if instead we just consider lapse by itself and then just the interaction between lifetime and offer here. So, all right, what's our final model going to be? What do we do here? So based on the work we've done, you would select your final predictive model as the one with the lowest estimated generalization error from build model, or maybe the one using the 1SD rule. So we'd be choosing between these 2 models. So, all right, which one are you going to choose? Well, it's up to you. It looks like that there's no, compelling reason to choose one versus the other from a statistical point of view. This model is slightly simpler because it only has 2 variables, but it's a little bit weirder in that the interaction appears, but the components of that interaction don't. So with predictive modeling, we don't really care what the form of the model is. It's just a hack job. So why don't we choose this as our final predictive model? Why not? It's the simplest one. Let's just go for it. So now that that's our selected model, it's fun to see, okay, well, how well did we do on the holdout sample? How well do different models actually end up generalizing to new data? So let's actually fit a whole bunch of different models and just see what ends up happening. All right, so what this code does is basically a lot of the work for you. Let's actually look to see how well the naive model does, the full model with all two-way interactions, and the model found with both of our searches. Let's see how well those models actually end up performing on the holdout sample, and just compare that with our final selected predictive model. So, all right, the naive model, we're fitting all of these guys just to the training data and then looking at their generalization errors on the holdout sample. So just running these commands here, get a whole bunch of outputs, just scanning through it. Let's just kind of see how well the different things do. So the naive model, all right, basically majority rules, we see that we would predict everyone to be reacquired. How many errors do we make on the holdout sample? We make 126 errors, or 74 errors on the holdout sample because we're predicting everyone to be reacquired. And so our misclassification rate is 37%. So all right, no model whatsoever gets us to a misclassification rate of 37%. Let's hope that our models that we selected do better than that. All right, so the model with just all variables in it, no interactions, how well does it do on the holdout sample? Well, we see we make 15 errors here, 12 errors here, for a total of 37 out of 200 for a misclassification rate of 13.5%. Way better than the naive model. So, all right, what about all two-way interactions in there as well? How well do we do on the holdout sample? Well, same misclassification rate. So, all right. What about the model found with the search, starting with the naive model? Misclassification rate, a little bit better, 12.5% on the holdout sample. What about the search procedure starting with the full model? Misclassification rate of 14%, a little bit worse here. So of all the descriptive models that we were searching for, the model actually found, starting out with the naive model, which was our selected descriptive model, actually also has the lowest misclassification rate on the holdout sample of the ones we've considered so far. So how well does our selected predictive model do? Do we do better than just the model selected during the AIC search? Well, let's go ahead and fit the model with the overall lowest generalization error if you considered all two-way interactions. So I let this command run forever, and this was the formula that results when you select the model with the lowest estimated generalization error while considering all two-way interactions. So let's fit that model and see what its generalization error is on the holdout sample, 14.5%. Actually a little bit worse than the model that we would have selected if we just done AIC search. If you do let all two-way interactions go and look to see at the model selected with the one standard deviation rule, the simpler model still within one standard deviation of the smallest error, it would be lapse plus age plus the interaction of lifetime times offer. How well does that one do on the holdout sample? 12.5%. So hey, that one's actually pretty good. That one ties our model selected with the search. And now finally, let's go through and look at how well the models that we're considering actually turn out to be. So what we saw way back up here was that based on our analysis, we were basically choosing between these two models. So let us fit the model with the lowest generalization error from part B, which is this guy right here, lifetime offer and lapse. So predicting reacquire from lifetime plus offer plus lapse, data equals train, family equals binomial. And then let's fit the other model as well, the model with just lapse and the interaction. So reacquire twiddle lapse plus lifetime colon offer without the components, just that exactly. So data equals train, family equals binomial. And let's see how well these two models that we were searching for, how they end up doing. Okay, so fit that model. Generalization error, 16.5%. That's actually really not that good. And the one that we really ended up selecting that we said, let's do the one standard deviation rule with just these two variables in it, how well do we do? All right, so our misclassification rate on the holdout sample is 15.5%. Are we okay with this model? Well, we compare the misclassification rate on the training data, the data that it was using to estimate the coefficients, to the misclassification rate on the holdout sample. And we want to make sure that our anticipated generalization error isn't too much smaller than what we end up actually seeing on new data. And this is a pretty small increase here from 14.3 to 15.5%. As long as that increase isn't more than 25%, you're more or less comfortable with using that model to make predictions on new data. So, all right, after all of this, what model ends up predicting the best on the holdout sample? Well, we found two of those models. The model found in the descriptive modeling context, the one found with the search starting with the naive model, and the model with, or the model selected with the one standard deviation rule when building the predictive model with all two-way interactions. The one that I didn't have you guys do because it takes way too much time, but the one from right up here. So with lapse, age, and lifetime times offer here, the interaction between those. So our selected model wasn't the best, but that's fine. With a different holdout sample, maybe it would have done better. To the best of our ability, based on our procedure, this would be the model that we ended up selecting. And it does generalize okay to the holdout sample, to new data. Sure, there exist models out there that end up performing better on that holdout sample, but who knows, maybe the selected model would predict better on different holdout samples here. And that's predictive modeling. We just kind of do our best with the data that's available to us and cross our fingers that it's going to be okay on new data. And this one seems to be all right. All right, so I feel comfortable with the predictive modeling, our predictive model being just these two predictors here, lapse and the interaction between lifetime and offer, since the error on the holdout sample wasn't too much bigger. It's within 25% of the error on the training data. All right, so that is activity 11.